All right, so big picture stuff. So this week we're doing chapter 8 only. So we have one chapter left before we go to the midterm, which will be next week. So we'll do a midterm review on Wednesday. So we don't have class on Monday. We have a review on Wednesday, and the midterm is on Friday. And you can and should go to the past year midterms, which is like definitely the easiest thing to study. It has all of them with all of the answer keys as well. So you can go check them all out, and they're on exactly the same material, and they're essentially the same level of expectation of what I would see. And you'll see also how much scribbling there is per question answer, so you'll have a sense. And what I normally do is I print out the answer key with just all of the answers converted to white text. So the whole that's there is how big the answer key answer is. So like you shouldn't need much more room. Like if you start thinking I need a lot of extra space, there's probably something that you're missing that makes it much simpler. So that's a clue to you about how the level of detail that I'm expecting. But I'll have scratch paper and everything else too, so you can certainly mess around and do other things, but it should be relatively short. Does that make sense? And so the homework is due on Friday rather than due on Monday, so that you have all of next week to just think about midterm stuff. And I had I assigned a few, made it a shorter, I stripped down a couple of questions off of it so that it's not quite as long as the other ones would be, or shouldn't be. That makes sense, everybody? And this homework will also be helpful in reviewing for the midterm, and that it covers a lot of the things that will be on the midterm as well. So this is not coincidental. Like what we do is we go up to cumulative up to this chapter and then whatever, and then after we will not go back specifically to revisit this material again for the final. The final is just on the second half of the semester, but of course we are building on all of the things we've done so far, so it's like the expectation is that you learn this stuff because you're going to be using it, but we'll be using it in a different way. We won't be coming back and doing like these style problems again. They'll just be built into other problems. Does that make sense to everybody? Okay. So the next thing we're supposed to discuss is vectors. We've already discussed vectors a little, but we're going to do it in a slightly different way this time. So when did we discuss vectors? I think I used the word a few times at least.
Complex numbers.
Complex numbers, we said that was kind of like a vector because it had direction and magnitude. That was good. And we talked about how there was only in 2D that it really worked as a vector because there's just an imaginary axis and a real axis. There isn't like a whatever, a surreal axis or something. That's the other one. So that was enough. And we also talked about vectors a little as the input to matrices. But in none of those cases did we really discuss the kinds of vectors that exist in our 3-dimensional plus 1 dimension of time world. And we also didn't talk about any kind of real, we talked about multivariate differentiation and multivariate integration, but we didn't do it in a way that's like really specific so much to our world. And so what this chapter, this last discussion is how do we think about the specific kind of vectors that we would actually use to build a geophysical framing for something that's in our world, and are there special versions of derivatives and integrals that are the most important ones in our 3-dimensional world? And there are. So that's really the structure of what we're going to go to. And it's going to come down to a lot of funny things like angular momentum or vorticity and these kind of things that you maybe have heard those words in seminars or in classes, but we're going to talk about the underlying idea why those things exist and what's special about 3 dimensions that makes this all work. Okay, so that's where we're going this week. And we'll see that a big part of that will be, so we had a fundamental theorem of calculus. What was the fundamental theorem of calculus? You know? short version. Yeah. So the integral is the inverse of the derivative, and the derivative is the inverse of the integral. And it's a little bit fancier with the Leibniz thing when we have the bounds of the integral. Like that's a little complicated, but those are flavors of one-dimensional fundamental theorems. We're actually going to see a fundamental theorem that's, we're going to see three different ones that are three-dimensional. And so that will, and those will be the ones that we'll actually use when we get to continuum mechanics to build the equations of motion. Because like, in the simplest sense, the way you think about it in an equation of motion is it's like, how much energy is inside of this box and how much energy is leaking out of this box? Oh, I could do an integral over a certain box and that would help me get started. But then in order to write the thing that's in the integral, we need a fundamental theorem of calculus to write it as a differential equation. And so that's the machinery we need to get to be able to talk about those kind of things. Okay. So what's a force field? Or what's a field? I always think it's funny to think of it as a force field because they have like clear sci-fi thoughts about what a force field is. It's like the thing that keeps like Luke Skywalker in. You touch it, it goes, right? But what is a field in general? Yeah.
It's some variable that's dependent on all three spatial dimensions and time.
Yeah, so it's something that depends on space and time, and every single point in the space has a value of that field, and it also has a position. So what's a field that we could use to describe this room right now? Temperature. So there's a temperature at every point. Temperature is moving. So if I was to define an axis over there in that corner, I could pick every point in this room and put a vector from that corner to there. That would be the position part of the field. And then there would be a temperature at that point. So if I write that down as, we hinted at this before, but we're going to be a little bit more careful about it. So temperature, x, y, z, t, or I could write it as temperature of a vector x and time t. Okay? So it has a position as an input. What kind of an object is this thing? Is it a vector? Is it a scalar? What is a vector and a scalar anyway? What are these things? We've been talking about them without being really careful about how they were defined. If position is a vector, what does it mean that it's a vector in this context?
Has a direction.
Has a direction and has a magnitude. So there's a distance from a point. And remember we were talking about all those strange things about linear operators and affine and whatever. We'll be a little, we'll be able to get down to that a little bit more. So if we have a coordinate system, we have a vector, it has a direction, and it has a magnitude. Okay? And then we talked about linear algebra being based on multiplying by a scalar. What do we mean by that? I multiply a vector by a scalar. We talked about this without really defining it. So now let's go back and think about what it meant in this context. If I multiply this vector r by a scalar, what does it do to the vector?
You're just changing its magnitude.
It just changes the magnitude, but doesn't change the direction. So this is also another vector. So multiplication by a scalar is allowed in a vector field, and the outcome and the input will both be vectors. So we could write this as this is some other vector. Okay. So what are some of the things that describe a vector? Like, so in the matrix multiplication, we had a matrix, and we were thinking about rows and columns, and so a vector was like a column thing, And one of the things that made it different from a scalar was that it had different elements, like multiple ones. So it's got like more stuff in it. A scalar has just one number in it. But because a vector has both a magnitude and a direction, it needs more things to describe all of that, right? The direction takes 2 numbers anyway, and the magnitude takes 1. So it's got 3 degrees of freedom in it, whereas a scalar has only 1 degree of freedom in it. That makes sense to everybody? Okay, so is temperature, so temperature depends on position, but there's a vector, and time, which we can take as a scalar for the moment. We're not talking about relativity. But what's temperature?
Scalar.
It's a scalar, good. Why, and why do you say that?
Because it's not pointing in any direction.
Doesn't have a direction, it's just got one number, doesn't have, right? So what's an example of a vector field? Temperature is a scalar field. What's a vector field?
Change in temperature.
Change in temperature. Let's think about that. So d by dt of temperature. Does that have a direction?
It could.
It could. So I'm deliberately being a little bit pedantic and saying that the change in temperature was a total derivative with respect to time. Does that kind of change in temperature is it a vector? Not quite, because it doesn't have a direction. It's still just a number. It's a different number than this number, but it's a number. But there's a different kind of derivative of temperature, a different way of changing temperature that does have a direction. What if I build a vector which is the partial derivative of temperature with respect to x, and the partial derivative of temperature with respect to y, and the partial derivative with respect to z? That has a direction, because there's 3 components. It also has a magnitude. I can sum the square of those, build a magnitude out of it. This is one of our special operations. And we write it with this funny upside down triangle, which is actually the reason why I'm teaching this class. I went to teach oceanography the first time, and I was writing this kind of symbol all over the board for like 2 weeks. And then finally, a brave student raised their hand and said, "I'm sorry, could you just remind us what that upside down triangle thing is?" And I was like, "Oh my God, I've been talking about this, assuming that everybody knew what I was talking about for 3 weeks." And so, anyway, we will go back. But this is like one of the most, in this version is called the gradient of a scalar field. And you can pretend that thing is like a vector that looks like this. It's actually not quite a vector, but we're not going to get too hairy into the details. It behaves sort of like a vector that has a hanging derivative. It's like a vector operator. So when acting on something, it takes a scalar and makes it into a vector. Does that make sense? That's the gradient form. We're going to come back to a couple of others in a minute. Okay, so this kind of change in temperature does produce is a vector. What's another vector that's maybe less weird?
Force of gravity.
Force of gravity is definitely a vector. Actually, all forces are vectors. That's one of the key things of Newton's laws, is that they're vectors. They have direction and magnitude. And so along with forces, we also have accelerations and velocities and positions. All of those are vector fields. So the force field of gravity in this room, the velocity of all the motion of the air that has these temperatures, also a vector field. The acceleration of all those air parcels is also a vector field. And the position itself is also a vector field, which is also a function of position, which is kind of funny because the position, but whatever. But let's think about what one of those has in it. So, I'm going to call it a different one. if v is our velocity vector, it also depends on position and time. Okay? So there's two kind of directions inside of it. There's a direction and a distance from the origin, that's the position part. But then there's also a direction, so we sometimes write it like, I might draw another little arrow. And that would be the velocity field at that point. So this velocity also has a direction and a magnitude. The magnitude is the speed, the direction is whatever direction this hunk of air is flying in. Okay, so that's starting to get clear a little bit. What I'd like to do is start talking about multiplying scalars and vectors together, and vectors together, and also building things. There's actually things even with even more than a vector. I could write two vectors next to each other and think about something that has two directions and two magnitudes at the same time, but think of it as one object. It's kind of like v times u of x and t. That object is called a tensor. And so we will get to that when we do, but we need a sense of multiplication. So we have equations like this equation. So this equation does what? It takes a vector times a scalar and it produces a vector. Everybody on board with that? So in an equation, just like we said, dimensions equals dimensions. Like we can't have length equals something to time. It has to be length equals length, or length per unit time, length per unit time. We have to have vector covariance, which means that both sides of the equation need to be the same class of field. We can't say a scalar equals a vector. Why not?
Doesn't have a direction.
Doesn't have a direction. So there's not enough information here to fill out what this side is. Or we can think of it just from our matrix multiply. This is a, we could think of the scalar as being just a 1 by 1 matrix, but then this thing would be a column. So that doesn't make any sense. Like which one of the elements is supposed to equal to that? So there's just not enough information in the scalar to fill out a vector field. Okay? But I could write some kind, maybe there's a kind of multiplication where I could take two vectors together and make them into a scalar. Does that make sense to everybody? So there is a kind of multiplication, it's called the dot product. It's written with a dot, like this. And there's we've seen this this is part of our matrix multiplication. If I took a row and multiplied it by a column, I would get the components plus the y component plus the z component is summed together. There's no more directions left in this. This is the way we do it in the matrix version. This is the way we do it like this. Okay, so there's something that's slightly deeper we want to get onto before we continue talking about this, which is there something else that we mean when we say this is a scalar, beyond it being a number? Okay? There is something else. What if I choose a different coordinate system? So instead of describing it based on the axis in that corner of the room, I describe it based on this corner of the room. I've just changed my conventions as to what I'm calling z and x and y. Does that affect the value of the temperature at this point? Does it affect the position vector I use to describe the position of this point? Yeah, for sure. Okay, here's the hardest one. Does it expect to change the velocity at this point? Sort of. It doesn't change it in value, but it changes the way you write it down, because we need to somehow express the direction in that new coordinate system. But there has to be a rule, right? There has to be, like, once I've said, here's my new coordinate system, there has to be like a transformation matrix or something that carries me from one coordinate system to the other. And there is. And for rotations and reflections, it's just a matrix. So if I take any vector in the old space, I can write it in the new space like this. And this will be a special kind of matrix. And I talk about how to generate those matrices in the notes. It's not so important except for the idea. And so the kinds of matrices we might put, or we might put a rotation into it. We might put a rescaling factor. We might switch from feet to meters. And we could build that into that. And really weirdly, okay, I've been very careful. We're going to start talking about right-handing rules this time. So when you pick a coordinate system, if it goes x, y, z, like on your right hand, that's a right-handed coordinate system. And if you do it with your left hand, x, y, z, you can't rotate them and make them work out. They're actually a mirror reflection of each other. So if you look at your left hand in the mirror, it looks like a right hand. If you look at a right hand in the mirror, it looks like a left hand. Okay? So in this coordinate system reimagining, I might be really complicated and decide that I want to mirror reflect my coordinate system as well as putting it in that corner. And that sort of seems crazy, but let's figure out. So if I do this one, I say that's x, that's y, and this is z. Okay, that might not be that crazy. But over in that corner, I could do it this way and have x, y, but z is down. But maybe I prefer to always have z up. So I still want this to be the x direction, this to be the y direction, but now I want the z to go up. That's not actually a right-handed coordinate system anymore. I can do that with my other hand and have it go x, y, z. Does that make sense? So it might be convenient in certain kinds of problems to flip the chirality of the coordinate system. And that's allowed. It's not we're going to talk about all the reasons why it will confuse you like crazy. The most important one is when you're sitting on your midterm, and if you're right-handed, you're writing with your right hand. And I see people doing this all the time, and then they start doing the right-handed rule with their left hand, and I'm like, no, no, no. You have to put your pencil down before you can do the right-handed rule. And whatever, anyway. If you're left-handed, it's easy, you can just do it. But anyway, so, okay. So if this is the coordinate change, which might be a rotation, might be a reflection, it might be a rescaling, to give me the new version of the vector, I'm not actually changing the velocity at all. I'm just changing the way I write down the velocity. So suppose I put the x coordinate in the place of the y coordinate. Then a vector that was 1, 2, 3 would become 2, 1, 3. And that's one transformation like that. And it's just because I've switched around which way I'm calling what. It doesn't change the nature, it just changes that. So everybody understand what I'm getting at here? So vectors do like this. Vectors need one of these to transform. What about scalars? What do I have to transform if I want to transform my temperature? Does the value of the temperature change? It doesn't have a magnitude, or it doesn't have a direction. So it doesn't have to change if I rotate or whatever, but the position inside does have to change. And I actually didn't even write that out for this one. We really should have said V old, which was a function of R old, and time equals R, which equals V new, times R new, and time, where R new is equal to R times R old. So I really should have transformed the thing it depended on too. And so for temperature, I would just transform the thing it depends on. But I don't transform the outer part. Okay? So in the notes I say this is the, if it quacks like a duck roll, which is a scalar is a thing that rotates like this, doesn't change under rotation and reflection. A vector is a thing that goes with one operation of a rotation matrix. Okay? All right, and here's a crazy thing. For the rotation matrices and the reflection matrices, their transpose is equal to their inverse. Okay, here's the super bonus question. What does that tell you about the determinant of this matrix? You can guess this. So remember the matrix inverse was 1 over the determinant times some crazy scramble of values. The transpose doesn't have anything like this out front, although it was possible that those might have been the scramble. So claim it's sort of obvious, not obvious. This would tell you that the determinant of that kind of matrix is 1. Or maybe minus 1. Because if the inverse has a prefactor of 1 over the determinant, and it doesn't screw this up, I didn't have to rescale the transpose side, that thing had to be 1. That's not exactly a proof, but that's close to the right way to think about how the proof works. Or it could have been minus 1. So the interesting thing about these rotations and revolutions and whatever is that if the determinant is plus 1, you can form it out of rotations alone. If the determinant is minus 1, it takes a reflection plus rotations. So if we want to go from a right-handed coordinate system to a right-handed coordinate system, we should be able to do it with a matrix that has a determinant of plus 1. If we want to go from a right-handed coordinate system to a left-handed coordinate system, we're going to need a minus 1 determinant to do it. And this will be the property of the matrix that does that rotation and reflection. Okay? All right. So can we use this fact to show that this operation means that this thing is a scalar? Steps in there. So, and there's one funny thing. So if I say this is the vector B, and it's like this, then the vector A is also going to be kind of the same shape. Does that make sense to everybody? However, if I just start calling those things vectors, those column matrices vectors. So when I write it like this times this, it's sort of like the dot product implies a transpose of the A matrix times the B matrix in order to get it to be a row vector times a column vector. Everybody sort of understand what I mean, at least in the matrix shapes? So when I write it this way, I would actually write it as matrix A transpose matrix B. So what if I want to transpose these two vectors into my new coordinate system using this rule? What do I do to B to transpose it and to make it in my new coordinate system? If it's B in the old, I would multiply by R, and then it would be B in the new, right? And A in the old would be A in the new times this R. So what's A transpose in the new? So if I want to figure out this thing, what's that? So if A in the new is this kind of a matrix, and A in the old is this kind of a matrix, and R must be a square matrix times it to make that work out. How do I transpose this equation and make it be the equivalent thing? I want to write this one like this, so that's that one. And I want to write this one like that too. But I can't multiply by a square matrix because that doesn't make sense, right? That isn't how it works. I have to write it this way. And so I claim that means that A old transpose times R transpose equals A new transpose. So when you transpose, you reverse the order of the matrices. Okay? In order to get the same operation just in transpose. Okay, so what does this operation look like then? If we take A old dot into B old, sorry, start with a new one. A new, B new, what's that equal to? That's equal to R, A old, dotted into R, B old. Everybody with me? So now I'm just rewriting it that way. But if I think about these as matrices, that's really going to be equal to A old transpose R transpose R B old. Everybody see how that works with this rule? Well, what's R transpose times R? It's the identity. Because for this special kind of matrix, R transpose is R inverse. Yeah?
Is that true for all transformation matrices?
It's not quite true for all transformation matrices. The rescaling factor is a little bit more complicated than just the rotation and reflection. The rescaling factor is also, you can write this whole thing with rescaling built in. It's just a little bit trickier to keep track of the determinant factor that comes in here, essentially. So this one would have a 1 over determinant, and this one would have a determinant. They would cancel again, but it wouldn't be so. It isn't as obvious as this. So, bing. That means that this equals A old dot B old. So look, I started with something that was a dot product. I transformed both of the vectors that went into it, and I ended up with something that's a dot product. So that's the same transformation rule we had for a scalar. A scalar doesn't change its magnitude when you transform the directions of the system. So the scalar product, this one, the dot product, the inner product, the scalar product, these all are different words for the same thing, which we write out this way, component by component, is unaffected by a transformation of the coordinate system. So it means that the outcome of this is actually a scalar. So that's cool. That means I can start writing all kinds of things. Because now I could consider a vector A times a vector B dotted into vector C. What kind of an object is that? Which part? Sorry, I didn't say dot. It said dot, but I didn't mean dot. This part is a scalar, and this is not. So it's still equal to a vector. So it's A times some, whatever, some scalar. Okay. So I can write equations that are scalar equals scalar. I can write equations that are vector equals vector. I can multiply those vector equals vector by scalars, which could be either their own thing or it could be a dot product of vectors. Does that make sense? We're building up these machinery. There's another one. Which takes two vectors and gives you a vector. And this one is called the cross product. And in some sense, it's very similar to the dot product. Does anybody remember the rule for this based on the magnitude of A and the magnitude of B and the angle in between them?
AB cosine theta.
So this is A times B times cosine of theta. And it really looks like a scalar like that because it's the magnitude and the magnitude, and then there's just a number that goes along with it. So this one, in terms of magnitudes, is defined very similarly. So take the magnitude. This is the magnitude of B times the magnitude of C times sine theta. So it's like the complement of this one. So if I had these, I could, build a right triangle out of these guys and talk about, with this side versus that side with this kind of thing. That's the kind of thing it measures. Okay? But that's only true of the magnitude. There's a funny business going on here with the direction. Because this thing actually has direction as well. So we'll learn our second right-hand rule. Okay, if I have a vector B and a vector C, what kind of a surface, what surface do they span in that space? It'll be a plane, right? So if I have B going this way, C going this way, there's a plane that they're in. So how can I make a vector from two things that correspond to a plane? Like what vector direction is left over after you've set up a plane? Perpendicular. So B, C, D. We don't know whether it's perpendicular out or perpendicular in, though. And so by convention, the cross product has a right-hand rule with it. You take your fingers, you start at B, the first one, then you wrap them around until you hit C, the second one, and the direction your thumb is pointing is the direction of B. So start, fingers pointing at B, curl them around to C, The direction your thumb is pointing in is D. And I just as well could have defined a left-handed rule and may define this differently. It doesn't, nothing breaks about the world, it's just this is the way that we do it. Just like we would prefer the right-handed coordinate system, which in some sense you could say X cross Y, Z. I'll use I hat, J hat equals K hat. Is that true? Maybe. So if I start in the X direction and go to the Y direction, Z direction is the right answer. What is the sine of the angle in between them? Sine is 1 because it's 90 degrees. And each of them have a unit vector magnitude. So this is an operation among the unit vectors that's useful to think about. That makes sense? Everybody? Okay, so the cross product is a little more complicated than the dot product because it's really kind of special to 3 dimensions. If I was in 4 dimensions and did this, I wouldn't have just a single, I'd have a plane that was perpendicular to the plane that those two were in, which is a weird idea, but there would be more room in 4 dimensions. So the cross product you have to be a little bit careful with because it's really specialized to 3 dimensions. And so even interpreting the cross product in a 2-dimensional plane, like if we happen to do vectors in the complex plane, there is something that's sort of similar to the cross product, but it doesn't have the same property that vector times vector equals vector. In 2D, it's actually vector times vector equals scalar. And in 4D, it's vector times vector equals tensor. So it's a little bit odd, the extensions of the cross product. And sometimes the cross product gets a little fiddly. But one of our fundamental theorems of calculus is going to be based on the dot product. One of them is going to be based on the gradient. And one of them is going to be based on the cross product. So we're already starting to get there. We need a little bit more of the calculus operations to build that up, but that's kind of where we are for now. Was there anything else I want to say on today? Oh yeah, let's do this fundamental problem. Take just like 2 minutes. How much sun gets to the earth? How much energy from the sun gets to the earth? And is that energy arriving a vector thing or a scalar thing? So here's the sun. I can make rings around the sun, and like the sunlight is coming out in all directions. So what do I know about the amount of energy that's going through each of those shells surrounding the sun? It's got to be the same unless something blocks it or absorbs it, right? So like the energy per unit area leaving the sun is not going to be the same as the energy per unit area leaving the next shell because the area is getting bigger. But integrated over that whole surface, that whole spherical shell, it'll be the same amount of energy per unit time. Does that make sense? So the power through each of those shells is the same. So we put the Earth in the way. How much does the Earth get?
Falls off the square of the distance.
Falls off at the square of the distance. And that one's easy to understand because how much bigger are those shells getting? What's the surface of a sphere? Or r squared. So each shell is an r squared. As r is getting bigger, the energy per unit area is getting smaller. Well, why am I saying this is a vector problem? What does it look like on the surface of the Earth? There's like sun coming this way, this way, this way, this way. So, is it the same amount of energy hitting here that's hitting there? Not in an area. Because the areas are getting longer the farther you're going down for the same perpendicular area. Does that make sense? So it's the same perpendicular areas, that would be the same amount of energy. But these are getting longer and longer and longer, like a little triangle. Does that make sense to everybody? And so the area that's on the hypotenuse versus the area that's on the vertical axis are different. So I claim, if you think about this for a little bit more, there's got to be a cosine of that angle factor, and that's going to tell you that you need something like a dot product of the intensity of light times a normal vector coming out of the surface. And I also claim that it's even simpler to think about is what if I just took a disk that had the same radius as the Earth, so all of them were hitting it perpendicularly. That one would be really easy to calculate because its area would just be pi r squared instead of 4 pi r squared that it is for the surface of the Earth. And so if you did do this and you did the integral, it'd have to be a factor of 4 that comes out of it. Does that make sense to everybody? Sort of. So this magic factor of 4 is very easy to forget, very easy to screw up, but it's definitely there. And so even though there's 1,300 watts per square meter arriving at where we are, roughly where the Earth is in its orbit, the amount per unit area that's hitting the Earth is actually 1/4 of that. So it's more like 300 and change watts per square meter that's coming down. Because the Earth has more area than the disk that would be casting the same shadow. And that has to do with dot product, that has to do with this operation having that cosine. Cool? So these kind of things are going to be really helpful when we're thinking about building geometric problems like this, where we're taking vectors and combining them to get scalars that we can integrate over surfaces and things like that. That's going to be the kinds of problems we'll start seeing in this sort of work. All right. Cool. So, take a look at the homework. The answer key should be up for the